we're going to wrap up the process context switch and process creation. And we are going to talk about the scheduling policies, which you are implementing in your lab 2. Right? So we'll talk about multi-queue scheduling policy, which we have already uploaded. So the slides we have already uploaded to ED discussion. So if you are interested to look ahead, right, you can find the multi-queue scheduling algorithm in those slides. Okay. Yeah, so the labs in this course are not too difficult. We have labs on scheduling. We have labs on synchronization, semaphores, how to implement semaphores, right? Slightly different from CS252, where you are using semaphores. Here we are teaching you how to implement semaphores. And then after that, we have labs on a simplified version of memory management. Right? So in the old days, when we take operating system course, usually you have a big lab that where you're going to implement a virtual memory management system. But nowadays, no one does that anymore. Right? So you still have a simplified version of memory management to implement. I think it's in lab 3 or lab 4, lab 4 I think, yeah. And yeah, labs. So the lab just requires you to do some garbage collection, which is much simpler than a full virtual memory system. And then lastly, you'll have some lab on file system. So what I want to see is that most of the topics that we cover in this course are traditional OS topics, right? And they will be transferable if in the future you are going to work on low-level systems, hardware and software. Right? So, but these things have been there for decades, and so I would be honest and see that the hot topic right now is machine learning systems. Right? So if many of the knowledge we learn from this course, I think in the future might be most relevant if you're going to work in machine learning systems. Right? So because OS related job positions are there are only a few big companies that really require OS developers, and yeah, but there's a lot of demand for machine learning system engineer and or what they call AI infrastructure developers. And many of the knowledge to learn in this course should be transferable to that context. So hopefully at the end of the course, maybe probably in sometime in April or end of April, you could get someone from the industry, NVIDIA or Meta, these big companies who work on machine learning systems to explain the current status, state of the art of machine learning systems, and yeah, so what you could, if you want to get involved in this direction, what you need to know. Right? So we'll see whether we can get someone to give a guest lecture, right, at the end of this course. Okay, and yeah, so if you're going to get involved in this machine learning systems, this area, I think eventually you'll find many of the concepts you learn in this course are relevant. Okay, all right. So process creation and context switch, right? So at the end of last lecture, we quickly went through how process is created, right? So the key is that you allocate the resources needed for a process, including its stack, and then you push items onto the stack to fake that this process has been switched off before. And so later, when you call resched, resched is going to switch in this newly created process. Okay, we'll quickly go through this process again. Right? So let me see. Right. Yeah. So this is a right. So this is how process creation set up the stack. Right. So before this point, you allocate the stack and related resource, including the devices for the process, and which we do not care. We will learn about them later, so we don't care about them right now. What is relevant is the process to set up the stack during process creation. Okay, and we went through this process, but it was pretty rushed. Let's go through this again. Hopefully, people can answer the questions. Right? So here we set up a stack, and we push stack magic onto the top. And stack magic, these kind of magic numbers, you will see them very often in computer systems. Anyone notice the other magic numbers in your computer? Do you know other magic numbers in your computer? Yes?
Usually with the size of an instruction, like 0x1.
Size of the instruction? Okay, okay. Any other magic numbers you see? Right, it's really a number that you put in on the storage system somewhere. Right. If you look into your file headers, right, your file ELF files on your Linux computer, you'll see that in these ELF files, in the header they have magic numbers. And in your disk, right, so the disk is separated into different sections, and each section also has a magic number at the head. So these magic numbers are often used to it's very special, often used to check whether you reach the boundary of the. Okay, but it's not that important. It's just it marks ahead of the starting point of a process, of the process stack in this case. Right? So you push a stack magic to the head, to the top of the stack, and then you push a bunch of arguments, right, onto the stack. And remember, I think we mentioned these arguments. They are, if you remember how process is created and started, right, these arguments are the arguments you use to invoke a function. Right? So, 1 second. Right? So when you create a process, you give the process creation function, let's call it right now, for using its name right now. Right? You give it a few parameters. One parameter is a function name or function pointer. It represents the function that you want to run using this process. Right? And then you give it a list of parameters, which means that when you use this process to run this function, what are the parameters that you use? Okay? So when you create a process, these arguments are the ones that you use in the process creation. Let me find a concrete example. 1 second. So this is when you create a process, right? So you run create, it creates a process, but also put it in a suspended state. So that's why you need to invoke resume, which we'll talk about later. When you call create process, you give it a few parameters. The first parameter is the function that you're gonna invoke. You're gonna execute in this process, right? This function. And so forget about these things right now for now, right? So this one, right? This char is the parameter you're going to use when the process starts, right? When the process starts executing this function. Okay, and then in the process creation process procedure, this is the arguments that they push onto the stack. Okay. You can imagine there's one argument in that previous example. So argument 1 is that character A. Okay. When the process is created, this A is pushed onto the stack. Okay. One question before your question, right? So what is this function address? Using the previous concrete example, right? The character A will be put here. What is this function address? Yes?
When you create a process, you have to have a function that you want to run. So that's the function.
Right, in the previous example, concrete example, it is that sendChar function. Right? In the previous concrete example, we showed there is a sendChar function which takes one parameter, a character. Right? That sendChar function, its address is pushed onto the stack and placed here. And that char, that capitalized A, that character, is pushed onto the stack and here. Okay. All right. Before we continue, sorry, the question.
Yeah, what is that S adder value? Where does it get added?
That's right. This is initialized to the top of the stack, right? So it's essentially pointing as you push items onto the stack, it just grows. Right? So it's a fake stack pointer. It's not a stack pointer register. It's initialized to be pointing to here, and every time you push something onto the stack, you increment it. You decrement it, which means that you're pushing items onto the stack. Yes.
The arguments, are you just storing the pointers or you?
The value. Right.
So
Yeah.
you always been random to
So in this case, that character, that capitalized A, that character is pushed onto the stack here.
Right, but is your code your conversions?
Sorry?
In your code, like, it is.
Let me see.
Your zero reference.
Sorry, I didn't fully get the question, but
Sorry, I thought you were just putting A as it was, but then zero reference.
yeah, just dereference. Right. Dereference. Okay. Right. A is put here, and that start function, that sendChar is put here. Okay. Right. And then after that, here the function address is put here, and after that, push the address of the stack magic here, and push the flags, push these general purpose registers. This part is to fake the stack for context switch. Right? Remember when this process is created, after it's created, in the future, the only way to get this process start running is through context switch. Okay? So in Xenu OS, you do not have another way to start running a process. There's no other way. After you create a process, the only way to get it run is through a context switch. So I want to pause here to explain a bit more. What does this teach us when we design complicated software? So this, I think, although this code, right, because Zing is a specialized educational OS, also real-world OS that runs on embedded systems, which in the future most of you might not be working on. But what can you learn from this? This is another lesson. Right? So when you are developing complicated software, you want to avoid the complexity to grow by reusing functionality as much as possible. Right? You design an elegant interface, in this case, context switch. Right? And you make sure all of the you make sure that it is reused as much as possible. Okay, so when the right context switch is used when you have a process that's in a ready list and you want to switch it in to run on CPU. Right? And it's also used when the process is just created. Right? When you create a process, you make sure its stack looks like it's just put onto the ready list, right? And you use context switch to switch it onto the CPU. Okay? So this is the design to reuse the one functionality. All right, so let's continue. Right, so here it pushes these items onto the stack so that this part of the stack looks like the part of the stack here after context switch. If you remember, this is how the stack looks like when a real process that has been executing got switched out. It calls rescat and push the parameters onto the stack and then push EBP, flags, and general purpose registers. This part of context switch, right, which is invoked after context switch, looks exactly like this part, right? Although we expanded the general purpose register, this part is just the general purpose registers. Right? But you can imagine they are the same thing. So in this case, after the process is created, right, during this creation procedure, context switch never got invoked, right? It never got invoked, but it fixed the stack so that it looks like the context switch has been invoked. And if in the future this created process is switched in, it will pop these general purpose registers and flags and the stack magic following here, the second part of the context switch function. Okay, I remember the second part of the context switch function here. It pops all the general purpose registers, right, and pops the flags and pops the EBP, and returns to the execution context of the new process that's scheduled in. Okay. All right. So I think probably this will be the last question to clarify the difference between scheduling in a newly created process and scheduling in a previously scheduled out process. Right? So the last question is here. Right? So when context switch finishes, when you return to the new process's context, in this scenario, right, in this usage case, what is this return address? And what is the execution context that you return to in this case, in the normal case? Yes?
The calling function,
Which calling function?
the function that call context switch.
Call context switch. Rescat. Yeah, exactly. Right. Rescat. You return to reset, and remember reset called context switch before it returns, right? And then you return to reset, which is here, and then you return from reset to the normal execution of that process. Okay. All right. Now, okay, so now the second part of this question is that what's different, right? So in process creation, when you schedule in a process that was just created, what happens? Which is the execution context that you are returning to? Right? In the normal case, you return to the old process, which called reset. Right? The old process was executing normally, and the timer interrupt got triggered, and the timer interrupt called reset. Right? But in this case, the process was just created. What is context you are returning to? The process never got executed. Trunk address, exactly. Right? So first I want to clarify, because the process just created, so in reality, there's no context you're returning to. Right? The process never got executed. It's not like the previous case where the process has been switched out before. So you really have a context to return back to. In this case, this process was just created. It was never executed, so you do not have a real context to switch back to. That's why here they put this function address here. Okay, this is to fix the execution context that you're returning back to. Okay, and this is the entry function of this process. The function that you put in the parameter of process creation. Okay, so in the previous concrete example, this is the function pointer to send char function. So after context switch, you pop all of these things out and you return to the beginning of send char function and start executing from there. Okay, so this is the entire process, how a process is created and how it gets started. Okay. All right. Any question about this? This is yeah. Let's see. This is the tricky part. At least when I was taking OS course in my undergraduate, I did find this context switch and how to create process trickier to understand than other things. The other concepts in OS are quite well defined, but here the context switch, it seems that there's a function, the context switch function, half of it got executed in the old function, and the remaining half of it got executed in the old process, and the remaining half is executed in the new process. It was quite a bit hard to understand for me. Especially if you have the other complexity here, when a newly created process needs to be treated slightly differently compared to a normal process. Okay. All right. Let me see. This is process management. So before we talk about scheduling policies, we'll need to talk about the process of suspension and resume before we move to scheduling. But okay, so we are let's look at this example again before we talk about the process suspension. You have a create system call that creates a process, right? But you always invoke this resume. Right? The reason is that in Xenu, when you create a process, the process is first initialized to be in a suspension, in a suspended state. It's not ready. Okay, and you call resume to start to really start running this process. Okay. Now let's look at how this suspension and resume is implemented. Okay. Right. Process suspension and resumption. Right. So the idea of suspension is that you temporarily pause or stop a process. So later, you still allow this process to be resumed. This is different from termination. Right? Previously, we talked about you can terminate the process. Right? But suspension is different. You are just pausing it. Okay. Right. So these questions, we'll think about them later. Now, suspension is simple. It simply means that you do not let a process to use a processor. Okay. When suspending, the OS must save the information about the state of the process, such as where it's executing, the content of general purpose registers, and set the state variable in the process table entry to indicate the process is suspended. Okay, so if you have followed what we explained previously, this part looks extremely like context switch. Right? You save the information about the state of the process. Right? This is what context switch does. And the only thing that's different is you set the state variable in a process table entry to show that it's suspended. Okay. If context switch is invoked through rescat, what happens? You are not setting it to be suspended, right? You are setting it to be ready, right? You are switching two processes. You're picking a ready process to switch in to run on the CPU, and you are switching out the current process running on the CPU and put it to the ready list. Okay. That's what you do in a normal context switch. But here, what's different is that if you are suspending a process, you are not adding the process to the ready list anymore. Okay, you put it in a suspended state. You do not add it to the ready list. Okay, so this is the only difference. Right? The suspension puts it in the suspended state, while normal rescat puts the process in the ready list. Okay. All right. When resuming, the OS must allow the process to use the processor once again and change the state to indicate the process is eligible. Usually, you change it to ready. Yeah, so here again, the suspend state is not ready, nor is it current. Right? Current means that it's using the CPU. Ready means that it's in the ready list. It can be scheduled or context switch to run. Okay, and all of the ready processes are organized in the ready list in memory. Okay, here. The Xenu code uses a constant process suspended to indicate a process is in a suspended state. Okay, so this is a diagram showing the stages or life stages of a process. You can have a process in a suspended state, and if you resume it, it will become ready. It will be added to the ready list, right? And if for a process that's ready or current, if you call suspend, it will be put into suspended state. Okay. Yeah, and only the suspended process can be resumed, and there are two system calls, suspend and resume. They handle these transitions. Okay. All right. The next question: how is a suspended state processes organized? Remember, the ready processes, they are organized in a ready list. Right, in Xenu. What about suspended? Do they have a list? Right. So in Xenu, there is no such list of suspended processes. However, the information about suspended process, meaning the general purpose registers and its execution context, are still recorded in this process table entry, just like the other normal processes that are switched out. Okay, and the process stack remains allocated in memory. What does this mean? Right? If it's not in any list, the implication is that whoever suspended this process need to remember this process is suspended and resume it. Unlike ready processes, for ready processes, you can scan this ready list to find them, right? But for suspended processes, you just need to remember which processes are suspended. And the other option is to scan the entire process table. Right? You have 8 processes. You scan the entire process table to find which ones are suspended. Right? But that's not recommended to do. Right? So you are directly manipulating the kernel data structure, skipping system calls. Right? So you likely want to avoid that. You don't want to directly manipulate the kernel data structures. Okay. All right. Yeah. So you probably, if you are suspending a process, you need to remember it and later use resume system call to resume this process. Okay. All right. Suspend. Self-suspension. Right. You just call suspend, get process ID. The suspension system call is very simple. It takes this process ID as its parameter. Okay. So what does it do? It finds its entry in the process table and set a state in its process table entry to suspend, and then call rescan. Okay. If it's in suspended state, it does not get added into the ready list. All right. So before we talk about suspension, let's quickly go through system call. I think at this point you should have a look at the enough number of system calls and know how to implement them. Right? System call is the operating system interface. It's a set of functions that the OS provided for applications to use. Right, so this is enforced in the commercial OS like Linux. Right, so system call is the API that the application can only use these system calls to access kernel functionality. In Xenu it's different. In Xenu you can actually get around system call. Right, so you can access kernel data structures directly without going through system call. But this is not recommended. Right? The whole purpose of OS design is that we have this interface system call that hides the the difficulty or complication of OS internal, so that you can use this system call APIs easily. Okay. Right. So the OS contains the functions that can be divided into two categories. Some functions are system calls, which means that applications can call them to access the kernel services. Other functions are merely internal functions used by operating systems. They are private to operating system itself. And we use system call to distinguish system calls. Okay. Right. So current execution of system calls, right? Multiple processes can attempt to execute a given system call concurrently, and concurrent execution can result in problems. Right? So we have discussed many synchronization problems, the data races. Right? So so we won't talk about this. All right. So when you implement system call, one thing that we can do to avoid synchronization, to avoid data concurrency bugs and data races, is by disabling interrupts. Okay. So what does this mean? Why disabling interrupt is able to prevent concurrency issues? It's explained here, but anyone can explain it intuitively. Why disabling interrupts can prevent concurrency issues? Yes?
Just because you're not going to be able to call focus.
Exactly, right? Concurrency issue, data races, they happen when two processes, more than one process alternate, take over execution. Right? One process was executing, and in the middle it switched out, and another process take over, and they somehow modify the same piece of data in their execution. So the second process modifies some piece of data, and the first process did not expect that data to be modified. That's essentially how most of the concurrency issue happens. Okay, and then because of that, the most obvious solution, right, disabling interrupt, right, it prevents a process to be scheduled out. If you disable interrupt, then this process will hold the CPU until the interrupt is enabled. Right? So, right. So that's how concurrency issue is prevented, and that's also why when you implement system call, you are recommended to disable interrupts in the beginning and enable interrupts at the end. Right? You want to avoid concurrency issue in the system call. Right. Right. So later we will explain interrupts in more detail, but for now it's sufficient to know a system call must use two functions related to the interrupts. The first one is to disable interrupts. The second one is to restore the interrupt flags. Right. Disable, it turns off hardware interrupts, and the function returns a mask value that specifies whether interrupts were previously disabled or enabled. Okay, so this design allows this process to remember the previous interrupt flag. When the process disables the interrupts, it does not just want to disable it. It wants to remember previously what was the interrupt flag. It might be disabled, it might be enabled. Because in the future, when you restore, when you finish executing this system call, you might want to restore the interrupt flag to the same as in the previous execution context. In the old execution context, if the interrupt was disabled, you want to restore it to the disabled flag. If the interrupt was enabled, you want to restore to the enabled status. Right? So the disable function does not simply disable the hardware interrupt, it also returns the old value of the interrupt flag. Okay? And restores the flag to the old interrupt flag before you disable it. Okay? So a system call usually use disable before or at the beginning when it's called, and use restore just before it returns. Okay. Right. So this is the slides that shows how system call is implemented. This slide was uploaded a while back, so I assume that most everyone has read it, right? So, and you could see that the system call functions in Xenu, they are all implemented like this, right? You have a mask, the system call including reset, suspension, they are all implemented like this. You have a mask, you disable the interrupts, and when it's disabled, you store the previous interrupt flag in this mask. Okay? And then after you executing this system call, at the end you restore the previous interrupt flag using this mask. And then you return from this system call. Right? Of course, in the middle, you have checks that checks the arguments correctness, and you also have error handlings. If error happened, you do some recovery or you report the error. Okay, and in the middle you do the real work for the system call. Okay. This is generally how you implement a system call. All right. Now let's look at suspend. Right. So you have this suspend function call. It takes a PID as its parameter, right? And it follows the template that we just looked at. You disable the interrupt and check whether the parameter is good or not, right? Whether the PID is good, is right or wrong, right? And here you never suspend the null process. Remember, null process is the idle process that got initialized in Xenu OS. Right? So you have an idle process. If you are not running any user program, this idle process should be running. Right? Yeah, this one is cannot be suspended. Okay. All right, and then you get these process tables, process table entry, right? And you, if it's in ready state, you change its state to suspend, right? Else you directly change it to suspend, and call reschedule. Okay, so this else means that it's in the current state. Right? If it's in current state, you just directly reschedule. Okay. When it's getting rescheduled, if it's in a suspended state, it will not be added to the ready list. Okay. All right. So that's suspension. It's quite straightforward. Resumption is not too complicated too, right? So let's yeah. So we'll quickly go through it, right? Yeah. Sorry, actually, we might need to come back to this later. Let's talk about scheduling policy first, because that will be needed for you to start working on the labs, right? So this part is we'll come back to it, but it's not that critical for your lab. All right, so CPU scheduling. We have hopefully, right, so at this point, everyone understand how the processes are scheduled. Right? So you have a ready list, and whenever the timer interrupt gets triggered, it's going to invoke reschedule to pick the process that has highest priority from the ready list and put it onto the CPU to run. Right? So that's how the CPU is allocated between the processes. Right? And every process it has if you look at Xenu source code, it has something called a quantum, which is a time slice it's allowed to run before it's rescheduled again. Right? So it's going to continue running for this quantum or time slice, and then it will be rescheduled, will be invoked again. If there is another process that has a higher priority, this current process will be scheduled out. Right? That's how CPU is scheduled between processes, how CPU alternates between processes. Okay. Now we're going to take a step back. Right? Why we need to do this and how to do it in a way that is helpful, right? So, okay. All right. So look at this diagram. Let me ask a simple question. Right? Why do we want to do this scheduling? If suppose we have two processes and both of them are simply just doing computation using CPU. Okay? The entire computation of these two processes are just using CPU to do some calculation. What is the benefit for us to do scheduling between these two processes? Yes? If both of them are only doing computation, right, is there even benefit? Yes, we are switching between them. Is there even benefit?
What was one possible CPU at a time? So, what you know, allow you to share the CPU resources between the two.
Why do you even want to share the CPU between the two? Does it help any one of them to finish faster? Right?
Right, so that one doesn't clog the CPU the entire time. Now the other one doesn't get to continue.
That's fairness. That's not helping any one of them to finish faster. Right? Yes.
Is it because not all instruction sets within a program necessarily need the CPU, so by alternating you can get tasking done that needs the CPU while other peripheral tasks are there?
Exactly. Right? The whole reason, what really motivated this multi-programming was that every program is using CPU for a certain amount of time, and you doing I/O for another certain amount of time. Right? So they are not doing CPU computation all the time. So if you have two processes, and you can schedule them in a way that when this process is using CPU, the other one is doing I/O. Right? And when this one is doing I/O, the other one can use CPU. This could help both of the process to finish earlier. Okay. If both processes are just using CPU, you switch between them, you can help with fairness. Right? But none of them can finish faster. Okay. In fact, if you don't switch CPU between these two, one of them can finish faster, can finish earlier. Right? If you execute one process before the other, one of them can finish earlier. Right? Alternating between these two only helps with fairness. But the problem completely changes if each process is not just doing CPU computation, right? It's doing CPU computation and I/O processing, right? So that when you have two processes, if you can interleave their CPU computation and I/O, then both of them can finish faster. Okay, so this diagram explains that. And this is the whole motivation of decades of research on scheduling policies and algorithms. So essentially, every process is doing different things, and you can interleave them. Right? They are doing different things at different times. Okay. All right. So so this is the typical execution of a program. Right? So it has some part of the execution that is a CPU burst, right? Which means that it's using the CPU to do some computation, or load store, add store, read from file. When this read from file is invoked, it does not do CPU computation anymore because it need to wait for this I/O to finish. Right? So this is where the program has an I/O burst. Right? It need to communicate with the storage device to get the data it needs. Okay, and then after the data is read, during this period of time, when it's waiting for I/O, the CPU, even if you give it CPU, it's not using it. Right? So CPU is idle. Okay, and after this I/O burst, then it gets the data it needs, and then it can continue to do CPU computation. So CPU burst. There's a CPU burst again. Okay, and then after that it does I/O again, and this alternates. Right. So this is the typical execution life cycle of a program, interleaved with CPU burst, I/O burst, CPU burst, I/O burst. And you can imagine if you have another process, and when this process is waiting for I/O, you allocate the CPU to the other process. Right? And when this process is using CPU, you ask the other process to do I/O. Right? If you do this, you are utilizing you are optimally utilizing your resource, and you can help both processes finish earlier. Right? This is the entire motivation of scheduling algorithms. Right? The intuition is not it's almost like it's almost trivial, right? As human, when we work on our task, we also do multitasking, right? So we let's say if you are cooking, right? So when you are boiling the water, usually you let it boil, and you're gonna cut your dishes and vegetables and prepare other things, right? So the spirit is exactly the same. The difficulty is that because computers are running so fast, right? So if you want to a slightly smarter design in a scheduling algorithm could save you a lot of time for the process execution. And so people put a lot of effort into optimize the scheduling algorithm even slightly, because it will yield a lot of benefit for process execution. Right? It's not like a human. When we do multitasking, we don't need that kind of optimal scheduling algorithms, right? Because in the end, the time we spend on the tasks are probably similar. But because of the speed of computer, right? Even a small optimization of scheduling algorithm in the end would manifest as big, very big benefit. Right? Does that make sense? So I think for many of the problems that you can learn, the motivation is the most important thing. Right? If you don't get the motivation, the solutions does not make sense. Right? Yeah. So some histogram of CPU burst times. So this shows that the CPU burst duration is typically very small. Right? A few milliseconds. That's the CPU burst of each program execution. After this, a few milliseconds, it's gonna switch to do I/O, and then it's gonna switch back to do this CPU for a few milliseconds, and then switch back to do I/O again. Right? This is the typical pattern of program execution. Okay. All right. CPU scheduler. Right. Short-term scheduler selects among the processes in the ready queue and allocates the CPU to one of them. Okay, there are long-term schedulers which we'll learn later, but yeah, this is a scheduler that you are going to work with in Xenu. It's typically called short-term schedulers. So it picks process from the ready queue and allocates CPU. Okay, this queue, ready queue, can be ordered in many different ways. Okay, and the scheduling decision take place in at different point in time. When a process switches from running to waiting, it switches from running to ready, it switches from waiting to ready, and then the process terminates. Okay. So we haven't talked about the waiting state, but it's essentially when the process is doing I/O, it's going to wait for the I/O result, right? So that is when it's waiting. Okay, running is a current process running on the CPU. Waiting is the process waiting for the I/O to finish. Ready is the process that's in the ready list, right? And terminates we have already talked about it. Okay. Right. Okay. Right. Scheduling under 1 and 4 is non-preemptive, which means that it is the process that is proactively giving up its CPU, right? And other scheduling, 2 and 3, is preemptive. It means that the other process that have higher priority can take over, can preempt the current running process. Right? That's what preemptive and non-preemptive means. Okay. When there is preemptive scheduling, you need to consider whether there is any concurrency issue. Right? You need to consider access to shared data, preemption while in kernel node, and interrupts occurring during these OS activities. When it's non-preemptive, it's easy, right? Your process just need to clean up whatever you are working on, and then you yield to the other process proactively. But when it's preemptive, when another process takes over, you need to be very careful. Okay? So, yeah, scheduling criteria. When we are talking about scheduling, we want to optimize for some goal based on some characteristics of the processes. Okay? There are some goals we might want to reach. Right? First is CPU utilization. We want to maximize the utilization of these resources. Okay? One is we want to maximize the CPU utilization. Right? So the CPU is always is almost never idle. We don't want wasted CPU resource. Okay? Another goal that we can optimize for is throughput. Right? The number of processes that complete their execution per time unit. Right? We can also optimize for this goal. Right? So very often, some of these goals, they are correlated, but they are not always equivalent to each other. Right? For example, you can imagine if CPU utilization is high, probably the throughput is also high. Right? Because if CPU utilization is high, probably means that many processes are making progress. So the throughput could be high. But they are not always equivalent. Okay. Turnaround time. The amount of time to execute a particular process. Okay. And waiting time. Amount of time a process has been waiting in a ready queue. Right? You wait for other process to finish. Right? And the response time. Amount of time it takes from when a request was submitted until the first response is produced. Okay. So there are different criteria that people use to evaluate scheduling algorithms. Okay. So you can try to maximize CPU utilization. You can try to maximize throughput. minimize turnaround time, minimize waiting time, minimize the response time. Okay. We're going to start from the simplest one, and we will directly jump to the multi-queue algorithm that you're going to implement in the labs. Right? So the simplest one, right, is first in, first come, or first come, first serve. Right? So it's called different names in different contexts. Okay, it's very simple. Right? So the first process you pick up, you solve, you schedule it onto the CPU, and you execute it until it finishes. Right? So we have process one. Its CPU burst time is 24 milliseconds. After this 24 milliseconds, it give up CPU is going to do I/O. Okay, right? This burst time means that after execution, it gives up CPU to do I/O. Okay, and then process 2, its burst time is 3. It takes the CPU for 3 milliseconds and then do I/O. Right? Process 3 the same. So if the processes arrive in this order, P1, P2, P3, then the first come first serve scheduling algorithm will arrange them on the CPU in this manner. Right? P1 will execute from time 0 to time 24, and then after that, P2 is going to be scheduled to on the CPU, and then P3. Okay, so the wait time for P1 is 0 because it's never in the ready queue. Right? It just directly gets scheduled onto the CPU and executed. The wait time for P2 is 24. It's waiting in the CPU for 24 milliseconds. And the waiting time for P3 is 27. You need to wait for P1 and P2 to finish before it's executed. Right? And the average waiting time is 17. Okay? Right, this scheduling algorithm is good for P1, right, but not that good for P2 and P3. Okay? All right. Okay, so suppose the process arrives in a different order, P2, P3, P1. We are still using this first come, first serve scheduling algorithm, and they are actually in this order, P2, P3, P1. And in this case, P1's waiting time is 6, but P2 and P3, their waiting time is 0 and 3. So the average waiting time is much shorter. Okay? Right? So the waiting time is much better than the previous case. Okay. So this is the previous effect, this effect where the short process arrives after long processes and got delayed because of them. It's called Covey effect. Right? So short process arrives behind the long processes. Okay. All right. So because of these downsides of the simple scheduling algorithms, so people have designed many different advanced algorithms. Shortest job first and the others, but we'll talk about them in our next lecture. But I want to quickly finish the multi-level feedback queue, right, which you will need to implement in your lab. Right, so you can start working on that. Right? So you can imagine in multi-level feedback queue, in the ready list, it's not one ready list anymore. You can imagine that this ready list is split into multiple ready lists. Okay, and each ready list, suppose this ready list is split into multiple queues, and each queue has their own priority. Okay, so for example, you have 8 queues, and the Q8 has the highest priority. Let's say give it priority 8. Right? Q7 has priority 7, and Q6 has priority 6. So all the processes in this queue will have the same priority. Okay? All right. So the scheduling rules for using multi-level feedback queue is as follows. The first rule is that if a process has higher priority, A larger than B, then A runs. This is similar to what you have observed in Xenu. Right? The process that has higher priority gets scheduled onto the CPU. Right? In this case, actually A and B are the same. Right? A is higher than C. A has a higher priority than C. So A gets scheduled before C. Okay. The second rule is that if priority A equals priority B, in this case, right, A and B are in the same level in the multi-level queue, it means that A and B will run in get scheduled in a round-robin manner. Right? What does this mean? It means that A is going to be executed for the quantum, the time slice is allocated, and when it finishes, it checks the ready queue. If there is a process in the ready queue that has the same priority as A, it's going to put A at the end of this queue and schedule B onto the CPU. Right? That's how you do it in a round-robin manner. A is running, but there is a process B has the same priority. You put A at the end of the queue and schedule B onto the CPU. Right? You do it in a round-robin manner for the process in the same queue. Okay. All right. Now it gets more interesting with the remaining rules. Right? So you want to adjust the priority. You do not want some process to be in the highest priority forever, right? Because in the previous process, if A and B stays in Q8 forever, then the C and D never gets executed. Right? They get stopped. Okay? So the intuition is very straightforward. If a process that has been in this higher level queue for too long, you decrement its priority. And if the process is in lower these queues for too long, you bump up its priority. Right? That's the intuition behind the later rules, but we'll look at these rules more closely. Right? So rule 3, when the job enters the system, it's placed at the highest priority, at the topmost queue. Okay. If a job uses up its allocation, right, the time it allocates while running, its priority is reduced. What does this mean? Right. What does it mean that if a job uses up its allocation? Right. Remember, a process can be scheduled out for 2 reasons. One is that it is still running using the CPU, right? But a timer interrupt happened, right? So its timer interrupt happened and checked. Okay, this process has been using CPU for the past quantum time slice. That's one probability. The other one possibility. The other possibility is that a process did not use up its quantum, its time slice, and it gave up its CPU proactively before its time slice was used up. What's the reason? It's going to do I/O. Right? If a process says, I'm going to do I/O, my time slice is, let's say, 2 seconds. I use the CPU for 1 second, but now I'm going to do I/O. This is when a process gives up its CPU voluntarily. Okay? So if a process gives up its CPU voluntarily, we do not penalize, we do not punish it. But if it uses up its CPU, right, the past 2 seconds, the time slice, it's been using the CPU all the time until it gets preempted. That's when we reduce the priority of this process. Right? We do not want a process to be in the highest priority for too long. Right? That's the first intuition we have. Right? Does this make sense? Right? If a process uses up its time slot, right? That's when we are going to reduce its priority. Right? But if a job gives up the CPU voluntarily before it uses it up, it stays at the same priority level. Right? We already explained this. If I want to do I/O, just 1 second, right? And I use only 1 second CPU, and I want to do I/O. I will stay in the same queue level. Let me finish this first. Right? Okay, so rule 5. After some time period S, move all the jobs in the system to the topmost queue. And what is the reason for this? Because as time goes on, many of the jobs, their process, their priority gets reduced, right? And there will be new jobs entering the system, and they will have higher priority. You do not want the old process to be stopped because of the new processes. Right? You do not want the processes that often use up their CPU to be stopped by processes that often give up their CPU. Okay. Right. So, so that's why after a certain amount of time, you're gonna change all of the processes' priority to be the highest. Okay. All right. Yeah. So there is also a different rule that you can try. Right. So once the job uses up its time slice at a given level, its priority is reduced. Right? So every process has a given amount of time at one level. You can also try this. Okay, so these are the rules that will help you to get started working on the multi-queue implementation. That's it for today. If you have other questions, you can come up and write down the names.